Hello everyone, Mr. Ford here, with a video for the textbook questions that you requested from the Part 1 homework from the Chapter 7 Momentum unit. So the first one we're going to jump into, actually before we do that, if you don't already have your online textbook available to look at, pause the video and go open that just so you can refer to the questions if needed. So the first thing we're going to do is question number 2. This is the question section. Where we have a light object and a heavy object have the same kinetic energy, which has the greater momentum, and explain. So there's different ways of going through this. You can do it like as a proportion and some lengthy comparisons, but I think the way the textbook does it, it's actually a pretty good idea. It's similar to what we did with unit analysis, basically trying to manipulate units to show what we have, show that something is an acceleration or a force, where we might not have those original units. So they start off by going through and saying, momentum is mass times velocity. And since kinetic energy is 1/2 mv squared, we know that the velocity portion of this equation is where we're going to be looking at kinetic energy, really. So the next step that they do is they just, manipulate the equation a little bit. They square the m, they square the v, and then they take the square root of it, which is still mass times velocity. So then they separate that out a little bit. They expand the m's. So an m times an m is the same thing as m squared times the velocity squared. And then they put a parentheses in here just to kind of show, all right, well, we're almost to kinetic energy. We have mv squared. We need the half. So how do we throw the half in there? So I'm going to move down here. So we need to get the half. But we can't just simply throw in a half. So if we put the half in there, we need to kind of cancel that out and put a 2 in there as well. So we're basically taking this equation and multiplying it by 2 over 2, which is still 1. Doesn't change the equation, but we can separate it out so that we can see that the 2 times the 1/2, and that 1/2 mv squared is the kinetic energy. So then that leaves us with our final equation of momentum equaling 2 times m times whatever the kinetic energy was. So looking at that, we're just comparing momentum, and we know, and this whole thing. So we know that, let's see here, the energy for both objects is going to be the same. They both have the same kinetic energy, so we're not worried about that. Looking in this equation, the variable or the coefficient 2 is there. So really it's just going to be proportional to the square root of m. So whichever object has a greater mass, that's going to result in a greater momentum, just because it's proportional by the square root of whatever that mass is. So I hope that was a little bit helpful, more helpful in just looking at the solutions and seeing, what was going on. The next question we have is number 3, which says when a person jumps from a tree to the ground, what happens to the momentum of the person upon striking the ground? So we still have to follow the law of conservation of momentum. So initially it appears the person has momentum as they're falling. They hit the ground and they are no longer moving, so they have no momentum. So there needs to be something that's moving to account for this transfer of momentum. So one way to look at it is that, things are moving, right? When you impact the ground, it makes a sound. So that sound is, vibrations of air molecules and then vibrating your eardrums, and then any other object that sound wave hits also vibrates. But that's not probably going to equate to all of that momentum. That'll account for a portion of it. So what's actually moving is the earth. So when you fall, you have two objects. You have you and then you have the earth. So you come to a stop, but then you and the earth move on. So it's kind of like, drawing a crude picture here. We have you plus the Earth, right? That could be the Earth. Let's put some landmass in here. And then in the end, you are now on that Earth, right? So it's an inelastic collision. So in inelastic collisions, here's our land masses. Put Florida in there. Kinetic energy is not conserved. So it makes it a little bit more confusing because we don't necessarily see one of our objects moving, or our objects that we've defined in our system. But we can look at it as maybe a little bit of mass from you. You have a big velocity. The Earth is at rest, no momentum. Then in the end, since you and the Earth combined, really mainly the Earth, has such a huge mass, the velocity is very small, insignificant, too small to even notice, just because the sheer mass of the Earth is so big. But, going like infinitely small, the Earth would actually move. The next question you guys asked for was number 4. And it says, when you release an inflated balloon but untied balloon, so you're just blowing up a balloon, regular party balloon, why does it fly across the room? So you blow it up, you let it go, and it goes all over the place, right? So again, this is kind of similar to the last thing. You have the balloon as your one object, and then you have the air, all as one object. So you have the momentum of the balloon plus the air equals the momentum of the balloon plus the air. So this is, again, another example of an inelastic collision. It's not necessarily a collision that we talked about, that kind of recoil type example, or explosion or explosive type scenario. So there's going to be an impulse, right? There's going to be a force because the balloon is elastic. So the balloon is going to push the air out one way. Then in return, Newton's third law says, balloon pushes on air, air pushes back on balloon. So you have the same impulse on each object, moving them in opposite directions with opposite signs of momentum. So one momentum is going to be positive, one's negative just because of their velocities. Let's see. Next one was 5. Explain on the basis of conservation of momentum how a fish propels itself forward by swishing its tail back and forth. So I'm seeing a kind of common trend here in what you guys are asking. So it's looking at that transfer of momentum when you might not actually see it. First off, jumping, you don't see the Earth necessarily move, but it does a minuscule amount. The air, you don't see the air moving, but it does. And then the same thing with the fish, you don't necessarily see the water move back. So you would have, in the beginning, you get your fish plus the water together, right, as your object or system. And then the fish places a force on the water then places a force back on the fish, then separating them. What did I call it? Momentum in the water. So the water actually goes back. So same thing whether you're paddling in a canoe, swimming, that water does go back the opposite direction. So the same kind of scenario. So that was all the questions that you guys had. Now we're moving into the misconceptual questions, where again, we're going to start with number 2. And we have a small boat coasts at constant speed under a bridge. A heavy sack of sand is dropped from the bridge onto the boat. The speed of the boat increases, decreases, does not change. Without knowing the mass of the boat and the sand, we can't tell. So the correct answer is B, decreases. So some people are going to think, oh, well, you had, it's like, law of conservation of momentum. You had the momentum of the boat plus the momentum of we can call it a sack of sand. and it turns into like a inelastic collision where things are combining. So since you had one thing moving um, horizontally, meaning the boat, and then the sack of sand not moving horizontally, it's more mass. That means it's going to slow down because it has that more mass. That's not necessarily the correct explanation, even though it does logically make sense. So the reason why that doesn't make sense is because the velocity of the sand and the velocity of the boat are perpendicular to each other. So those velocities, it's not necessarily a linear collision. So the reason why the boat is going to decrease its speed is because of friction. So if you have the boat, don't laugh at my drawing. Oh, that was really bad. Let's get water in here first. And then you had this like sack of sand falling, right? Once that sand comes in contact, and the boat's going this way, say to the right, the sand is moving vertically. So once that sand comes in contact with the surface of the boat's moving horizontally. The sack of sand is not. So the sack of sand wants to keep on going down, but which way is it going to go? It's going to move along with the boat because of friction. So that little bit of frictional force slows down the boat. So you have the boat wanting to go to the right, that frictional force goes the opposite direction because of just simply the inertia of the sack of sand. It's kind of like that tablecloth trick where you have, nice organized dining room table and you have your tablecloth and you pull real fast and everything stays. Well, if you go too slow, the inertia of those objects, resist the motion and there's friction there and they will then, move with the tablecloth. It's kind of that similar idea here. But it's not because of conservation of momentum. It is, well, partly it is, but it's not a collision type problem. It's the fact that we have a force, a friction, which is creating an impulse, which is transferring that momentum. So the horizontal motion of the sack of sand is initially 0, and then it will be some horizontal velocity because it's going to move along with the boat. So then we had number 3. So we have 2 identical billiard balls traveling at the same speed, head-on collision, and rebound. So it's an elastic collision. If the balls had twice the mass but maintained the same size and speed, how would the rebound be different? So it's just, momentum of object 1 plus the momentum of object 2, and then they remain separate. So the speed is staying the same. So if we're thinking like mass velocity plus mass velocity, we can put 2's in there. Oops. So nothing's going to happen to the speed, but they're going to be twice as massive. But both of the objects, both billiard balls, are going to be twice as massive. So if we just simply put in like a coefficient here, 2, masses are all doubling, it's a mass party for 2, right? Everybody brought 2 to the party, so that gets canceled out. And it's the same scenario as it started with. By putting in but maintain the same size, that's just a distractor. The size of the object does not matter. It's the mass of the object. So we're going to have C, no difference. Number 5 of misconceptual, we're here. A space vehicle in circular orbit around the Earth collides with a small asteroid which ends up in the vehicle's storage bay. And we have to say, for this collision, is momentum conserved? Is kinetic energy conserved? Is both kinetic energy and momentum conserved? Or is neither momentum or kinetic energy conserved? So first off, momentum is always going to be conserved in a real scenario, at least within the range of this physics course. However, kinetic energy, a specific type of energy, doesn't have to be conserved. The total energy can be conserved, but a specific type doesn't have to be because it can change form. So basically what this is saying is we have essentially a box. I'm not going to get detailed and draw a rocket here, sorry. We have a rocket moving, or no, yeah, a rocket that has like a cargo bay, basically a box. And then you have this, I don't know, how are we going to do it? This asteroid that's moving. And then they're going to hit and then get somehow trapped inside. Maybe they planned it, take it back to Earth. So it's going to be, this is we'll say rocket, momentum, asteroid, momentum of the rocket and the asteroid. So that would show conservation of momentum. However, like we've discussed in a couple other scenarios, since now these objects are moving off together, they're going to move off together at a slower velocity because their mass increased. So the momentum is going to be conserved, but not the kinetic energy. So, and that's also another thing that you can kind of memorize, that in inelastic collisions, kinetic energy is not conserved, for the main reason that we know we have things hitting each other and there's no give, there's no bouncing. So that means that particles are going to either come off and break, there's going to be sound, and all those other things that we talk about is where that little bit of kinetic energy goes. I think that's all parts of that. Yep. Then one more. We got number 6 of misconceptual. We have a golf ball and an equal mass beanbag dropped from the same height. They hit the ground. The beanbag stays on the ground while the golf ball rebounds and bounces up, which experiences the greater impulse from the ground. So this goes way back to one of the first things we looked at with the clay ball and the bouncy ball. So just an overall concept. When things bounce, there is a greater change in momentum, therefore a greater impulse. So that was that first kind of discussion of impulse. So the beanbag will go from some velocity, right? They'll drop from the same height, so we know when they hit the ground they're going the same speed because of acceleration due to gravity is the same. Everything falls at the same rate. So they hit at the same speed. So they had the same momentum when they hit. But the beanbag went from that momentum to 0. Whereas the golf ball had to go from some momentum or some velocity to 0 and then back up the opposite direction. So a greater overall change. So if we looked at the velocities, if, say it went from 5 to, for the first case, the change in velocity with the beanbag might be, from 5 to 0. So a change of 5. But then for the golf ball, it may have went from 5 down to 0. So we're subtracting, right? It's a change. Back to 5. It's going back up the other way. Or even if it was some energy was lost and it was something smaller, it really doesn't matter. It's because they're going opposite directions. So if we had a positive 5 direction, meaning down, if we call down positive and it goes back up, it would be an overall change of 10 meters per second. Or we can even look at like units of momentum if we wanted to. So the golf ball has the greater impulse because it had a greater change in velocity, therefore a greater change in momentum. And change in momentum is equal to impulse. So one more thing here, we got a problem. and there was only one that people wanted to look at, and it was 35. So let's take a look at 35 here. So we started this in class. I sketched out a diagram a little bit for you guys. And so we have this bullet moving. It's 28 grams, but we already know that we're going to probably have to convert that. So 0.028 kilograms. And it's traveling at 190 meters per second. And then we have this pendulum, and it's a block of wood, where this mass is 3.1 kilograms. The length of this string is 2.8 meters long. And I'm going to move that out of the way. And once the bullet embeds itself into the block of wood, right, it's not going to go all the way through. It's going to swing up to some maximum height. And at that maximum height, the velocity is 0. All right, so this is quite an involved problem, or not really. It's essentially we need to see that the first part of this, right, is here. Here's our collision, our inelastic collision, where we need to figure out how fast the block and the bullet are going to move off together. And then it turns into an energy problem. We're going to take that kinetic energy that the block has when it's starting to move, and then it goes up to some maximum height. So it's kinetic energy into gravitational potential energy. So it's not too complicated. The final part of this question is fairly simple. It just sometimes it's a little bit harder to see. So we're going to have the momentum of the bullet plus the momentum of the, actually, what are we going to call this? Bullet and block. This says pendulum. Why not P? So the bullet and the pendulum. And then they're going to be together, so it's inelastic. There we go. So we have the mass and velocity of the bullet, the mass and velocity of the pendulum, and then that combined mass of the bullet and the pendulum, and then they have the same velocity. Okay, so we can just fill in everything that we have here. Let's see, mass of bullet, 0.028. And notice the comparison between the bullet and the block or the pendulum is fairly significant, right? The block is a lot bigger in mass. And this is going 190. The block is not moving, so no momentum. The mass of both added together is going to be 3.128 kilograms. And we're looking for this velocity. So we plug that into a calculator. There we go. And we get a velocity of the bullet and the pendulum of 1.7 meters per second. Which is still kind of fast, right? It's like almost two meters in 1 second. So this thing's kind of moving. So we're going to look at the kinetic energy here going to gravitational here. So that's our next part of our problem. Kinetic to gravitational, so 1/2 mv squared we could see it's a mass party. But just note, if you were to plug in the mass, it would have to be that combined mass of both objects. So that's gone. So 1/2 our velocity that we calculated. I'm going to use 9.8. And then I can solve for the height. And I get a height of that. So that's my vertical displacement, right? That's how far it's going to go. So if we again, I'm just going to sketch this down here. Our pendulum's here. Again, this length of string is 2.8. Yeah. From here to here. And also, this side is 2.8 as well, from here to here. So this went from some zero mark, and it is now up, whatever this would be. I'm just going to go to like, try to make it easier this way. To keep it a little bit simpler, we're going to get rid of the boxes and just have a point. Cool. So again, this whole length, 2.8 meters, that whole length, 2.8 meters, it went up. This might not be to scale. 0.147 meters. So how do we figure out this horizontal part? From here to here, we need the horizontal component. So part of the difficulty is we're thinking along the ground. And really what we're looking for is just from here to here. And we have a triangle. We have a triangle. So if we know this full height here was 2.8, and we have a portion of it right here was the 1.47, or not 0.147, we can figure out this missing piece, this piece here. So if we just subtract that, zoom in a little bit, 2.8 what are the colors here? This missing piece is 2.653 meters. So we have a side, hypotenuse. We can figure out this missing side from Mr. Pythagoras. So if we do a squared plus b squared equals c squared to get that missing side, so 2.8 squared minus 2.653 squared equals, take the square root of that. Oh, I guess I should be plugging that in my calculator. I'll write it down, why not? And it's 0.895, so we'll call that 0.90 meters. So we have our horizontal, and we have our vertical displacement. So going right from the beginning to this, we wouldn't have seen until we started to sketch this out and draw it, and seeing that we have pieces of all of these different lengths, and then we can figure out the what the question is asking us. So hopefully that helped. If it didn't, make sure, or if there's additional questions, make sure you come to office hours or let me know next class, and we can go over them.